All right, if we drop a bowling ball on a spring, so I'm kind of picturing that mattress commercial that used to be out there. Lady held a bowling ball way up high. We had a spring down here. Oops, that's a terrible looking spring. Let's try that again. We had a spring down here. That's a bit better. The bowling ball is going to fall the 2 meters till it hits the spring. And then it squishes the spring some distance. I'm going to call that S again. So after the fact, the spring would be more squished up. Again, to solve this question, it goes back to concepts. What's the concept if we drop a bowling ball onto a spring if we want to find the maximum compression of the spring? This is another energy question. As the bowling ball falls, it starts off up high with gravitational potential energy. As it falls, it gets going faster and faster and faster. Then as it hits the spring slows it down to a stop, absorbing those joules and storing them in the spring. For what we're asked here, I don't care about how fast it's going, so I can just jump from mgh, ignore the 1/2 mv squared in the middle, jump straight to 1/2 k s squared. Now it's a matter of plugging things in and grinding them out. We've got a 5 kilogram bowling ball. G is always 9.8. A common goof up here is that H doesn't stand for how far the ball free fell, it stands for how far the ball moved vertically. So a common trick in this one is that the H isn't 2 meters. The H is actually the 2 meters plus S. It wasn't free falling for that last bit, but it was still getting lower, and since it was getting lower, it was losing gravitational potential energy. That's going to be equal to 1/2 k s squared. This is going to turn into a quadratic. 5 times 9.8 times 2, that's 98. Distributing that in there, 5 times 9.8 times s is 49s. And 1/2 of 500 is 250 s squared. Putting that in standard form, 250 s squared minus 49s minus 98 equals 0. I did this one kind of quickly. I hope I didn't goof it up. I got an S of positive 0.73. That's the answer we're going to take. That's how far the spring got squished. When you follow through the quadratic formula, it gives a second answer, negative 0.54. We saw this in projectile motion. Similarly here, the physics doesn't understand the context of the question. If we were to drop a bowling ball onto a spring, it would squish the spring 0.73 meters, and then that's the maximum squish. At that point, the ball stops for a split second, but then the spring pushes the ball back upward, and the ball would vibrate up and down over and over again. We're going to talk about harmonic motion in a few days. What the 0.54 is if we just let the bowling ball, if it somehow stuck onto the spring, the bowling ball would vibrate and end up, if it didn't get fired off the spring, it would get that other distance s above the normal length of the spring before the bowling ball stopped again. So if the bowling ball, maybe if it was made out of clay, if a 5 kilogram clump of clay fell on the spring and stuck to the spring, it would squish the spring downward 0.73 meters, stop for a split second, then go up through that middle point, and it would go up an additional 54 centimeters and stop for a split second, and then wobble back and forth between those 2 points. It's not completely symmetrical since gravity's downward. It's going to get squished downward 73, but then only get pulled upward 54. So the 54, the way it's worded in this question, is not necessary, inadmissible if you want to call it that, but what it does represent is if the ball had stuck to the spring, how far the spring would have gone,